But we have a soft drink company, Coca-Cola or Pepsi, something like that, or some local bottler. They're monitoring quality of their beverages in terms of clarity. Clarity is important, right? People like to look at a bottle and see straight through it, see how bright it is. Samples are visually inspected and marked accept if the sample is translucent and reject if the sample is cloudy. I don't know what would make soda cloudy. I guess there could be a bunch of different things. It depends on what it's made out of, right? If you had like a cherry soda, maybe you didn't filter out the cherries good enough or something like that. Anyways, previous data has shown the fraction of cloudy bottles per lot is 0.05. So our first question is, how large should the subgroup size be for a 95% confidence interval and a desired precision of 10%? So I think we have everything we need to figure out what our subgroup size should be. What's another term for subgroup size? Sample size. I'm sorry, but it's just the semantics. You deal with this in science all the time. You're like, why can't you just call it sample size all the time? Why can't you just call it subgroup size all the time? But that's just the reality that we're living in. You go back and forth. So, but with experience, you'll just pick it up. Okay, so anyways, we want to solve for n. Didn't it say n equals p times 1 minus p times, wasn't it just the z alpha divided by 2 times e, where e was p times desired precision. So first question, do we have p? What is p? 0.05? Yep. Equals 0.05. You know what 1 minus 0.05 is? 0.95. We need to look up z of alpha over 2. It's going to be 1.96, which is right here. I've written over it now, but this is 95% in the second column. Can you see that? We're looking over here, 1.96, okay? And we need to divide that by E. And here we go. Don't make this mistake of only punching in, the desired precision. We got to multiply these two. So we're going to put in 0.05 times 0.1. And I get 18.62. And you can't have a fraction of a sample, so I would just round up to 19. So we've just accomplished step 2 in constructing a control chart. Remember, step 1 is figure out what you care about, and then step 2 is figuring out how many samples you need. You'll see on the next couple of slides they have way more samples than 19. It's like in the 200s. But this just tells us if you want a 95% confidence interval, and you know what confidence interval means, right? It is what it sounds. How confident do you want to feel? Do you want to feel 95% confident or 99% confident? And if we look at that table of values, you can see the z value gets larger as we go up in confidence. And it makes sense that you would need more samples if you want to be more confident, because this z value is in the numerator. So if the higher, like if you wanted a 99% confidence interval, z is actually 3 or something like that. So you would need more samples. So depending on how risky your operation is, you know, how risky a faulty attribute would be, take more samples. Okay. So we just answered this one, 19. And next, we're going to calculate the central line. So here's what a p-chart data set example would look like. We have How many subgroups? 25. Now, let's look at the second column. You understand this is split in half, right? Just to make it so you can see it on one slide. Ideally, we would have shown 13 through 25 underneath 12. Anyways, the second column is N. Notice how they go from 225 to 200 to 275. It's not a constant sample size. And that's why we're working with the P chart instead of the NP chart. Recall if we go back a few slides, right here, we're going to use NP if we have a constant, but we're going to use P if we don't have a constant sample size. Okay? That's the only difference between the concepts of P versus NP charts. Okay. Now, what is this next column? Number nonconforming. So for that first subgroup, we inspected 225 bottles of soda. Could you imagine that? That's a lot. So you see the math of how to get the proportion nonconforming, which is the third column here. This is P. P equals 22 divided by 225. It's actually 0.098. But you get the point. We rounded up for this example. That's how to get P, individual P, not the average P, not the P bar. So if we look at our formula here, notice how for this P bar, we're going to divide the sum of NP by the sum of N. And we're going to do that for the individual P as well. For the individual P, it's going to be the same thing, except it's not the sum, it's just the individual. And that's what we just did. We took the 22, this was 22 divided by 225. Okay, so it's really not complicated math. If N was constant, we wouldn't need this third column. We would just chart the number nonconforming, NP. We wouldn't divide it by N because there's no need to standardize it. But this example is a pain in the arse because its sample size is constant, and I'll show you why that's complicated if you have a unconstant sample size here in a little bit. You see where we're going with this, right? We need to calculate P bar. You could do that, right? How do we calculate P bar? Well, we're just going to add up all of these P's, 0.1 plus 0.11 plus 0.06. We're just going to sum up NP divided by N. Based on that P bar, you know where we're going with this. We're going to calculate those control limits. Easy math. Easy peasy.